ZisK is the ZKVM that we have been developing for the last year in Polygon. Mainly what we have been doing is using all the technology from Hermes, Polygon, the ZKVM, all the knowledge that we accumulate there. I mean, on all the experience that keeping ZK prover in production gave to us. I mean, from security perspective, from learnings, from things that work, things that don't work, things that are performant and not. And we took all this technology. Actually, we improve a lot. We rewrite all the PIL to PIL 2. And from the last year, we start building the ZisK project. I mean, ZisK is a ZKVM. As you know, you can, I mean, it's a RISC-V 64 bits. Emulation, so you can write programs in Rust. You know better than me. I mean, you write the programs in Rust, and then you just prove them. Okay. Proving in real time. I mean, probably this is not new to you. Why is important proving in real time? I want to mention here two applications. One of those is connecting networks. This is what in Polygon is the aggregation layer. Okay, but I mean, in a more generic way, if you want to connect one network to the other, you need to prove fast. And if you want to connect them, the idea is that the other network needs to be sure that that the state is committed and valid. Okay, so if you have two chains, maybe you can follow the chain, the other chain, and that's fine. But if you have thousands of chains, all the chains cannot follow all the thousands of chains. And in an environment where chains are created and not created, this doesn't work. And so the way to do is just instead of following chains, actually the chain generates ZK proof, and then all the other chains can use this information to validate the chain. Okay. And the other application is very much for new consensus algorithms. I mean, here the Ethereum Twin chain is an example of these chains. But when you are introducing the ZK in the consensus technology, then you open a new era in the consensus chain. So there is other applications, but this is one of the motivations. And all of them, they require to write fast proofs. Okay, and fast proofs. So that what we did mainly is just design from scratch. Is okay. We take this thing. We have this technology. What can we do to accelerate? I mean, how much can we push to have a fast proof? Okay, and this is very much where we get. Some considerations in the ZK. So of course, fast proof. We are controlling the full stack. I mean, the idea is that we go from the very low level. Primitives to the high level, so we control the proving stack. Mention that the ZisK is we built a full prover, okay, and ZisK is just like it's another circuit of the full prover, okay, so it's a full technology that we are hierarching from here. We are targeting 128 bits. I'm emphasizing that because, I mean, I see in this space that, okay, we are giving away, and many projects are doing 100 bits. Again, if we decide we go to 100 bits, let's reduce the security to everything to 100 bits. But if the standard is 128 bits, which I think we all agree, then let's stick to 128 bits on that. Because if not, we are cheating ourselves on this. Okay. We are also full open source. We are very committed to open source. I think that if you are in this space, you know that everything that's not open source, we cannot trust that. So we are open source from the first day. We are developing open source. You can go to the code. You are seeing the branches that we are doing. You are seeing the modifications that you are doing. We are developing open source, and we believe in these values in open source. And open source from the beginning to the end. I mean, including the proving systems, the tricks, and whatever. We believe in learning from other projects. I hope that other projects are also learn from us. We want to be part of the space in a contribution space. So it's open source to the limit on that part. As I mentioned, it's a 64 bits. People may ask why 64 bits and not 32 bits. Well, I mean, the difference is not like something huge, but the performance is that, well, first, when you have a 64 bits, the number of instructions you need to run is less. So, and if you matter is the execution time and latency, this is an important thing. But also you are saving, especially Rust, where it makes the big difference is when you are transferring, when you are mem copying. I mean, Rust does a lot of moving data around from one side to the other, and moving in at 32 bits at a time or 64 bits at a time would just improve a lot. So it's maybe just going to 64 bits, having an improvement of 20, I don't know, 20, 25% probably is a good thing. Also, 64 bits allows you to work with other compilers, for example, Golang or even C# or other compilers that they are not LLVM based and they have some direct 64 bits. It's more standard. I mean, the current standard in compiles in today's day is not 32 bits. It's more 64 bits. And 32 bits was more in the maybe in the 80s. Not now. Well, and as I mentioned, ZisK is quite modular. I mean, it's a full proving system. So ZisK is just an example on that. These are the current timings. I mean, here is where we are, okay? So we divide the proof computation in 4 parts. The first is the execution part. The first is probably the one that's the most limiting because it's the one that you cannot parallelize. And so mainly what we do here, instead of let's say, interpreting the RISC-V code. Actually, what we are doing, we are like pre-compiling. I mean, we are converting RISC-V to Intel instructions. So we can do that really, really fast. Actually, currently, the current numbers is that we are able to execute this code plus creating what we call the minimum trace. I mean, if you need to create a proof, you need to extract something from this computation. This is what we call the minimum trace, because from there we can already divide by chunks and execute in parallel. Okay. At this point, with a machine, I mean, let's say, well, this is with one of our developers' gaming machine. Okay, so this is about a 5 gigahertz machine with a fast memory. I mean, it's a quite fast machine. We're already at 1.5 gigahertz executing. So that means that if we do overclocking and maybe with the new functions of being able to be at 2 gigahertz, probably it's feasible at this point. Okay, so that means that we are very close to native execution with this. Okay, so doing this part, we are good. The next part, this is the witness computation. Okay, we extract that, but now we need to write the actual witness. Okay, we need to write the polynomials from this part. This is the part that we have been, let's say, working less. That's the one that we are working right now. I put it in red because 6 seconds, but we believe that we can improve that maybe to 2 seconds or something like that. By the way, this is just to prove a block that has 35 million gas, 230 transactions. This is the block number. And here we are using 32 GPUs in 8 hosts, so 4 GPUs per host. Okay, so these are the timing. So this 6 seconds going to 3 seconds. I hope that in the coming weeks we can reduce that number. The next one is air building. I mean, this is where the real work is happening. This is what happens mainly in the GPU. The first one happens a lot in the CPU, but the second one happens in the GPU. The good thing of this is that this is the big work, but this scales very, very, very well. I mean, this parallelizes very well. This is with 32 bits, so you can expect that if instead of putting 32 GPUs, you put 64 GPUs, this number is going to have. Witness computation, it should, but at this point, it does not parallelize as well, but theoretically it should. Okay, so these 2 things should parallelize well. Okay. And the last one is the aggregation part. I mean, we did also very important work. Right now on aggregation, it takes 150 milliseconds just to aggregate. But not only that, I mean, in a single GPU, we can build, I don't know, something like 16 at a time on that. So aggregating all this at the end is log-n. I mean, if you have right now, this proof I think was something like 500 errors that we need to prove. So this is 2 to the 9. So this is 9 times 0.15. This is maybe it could be 1.5. Put here an extra margin, but this is more or less where we are. So if you see these numbers, we are more or less at real time, especially if we reduce these 6 seconds to maybe 2 seconds, we definitively are going to be in real time. Future points, optimization. I mean, still some optimizations, pending optimizations, especially in the memory part. There is some optimizations needs to be improved in that part. Okay, we need to finish also the BN128. That's almost finished in there, but we have some, of course, some documentation and cleaning and prepare very much for the audit. I mean, auditing, when we stabilize more or less this, we need to audit that so that this can be used in production ready. We're gonna start probably with we're gonna start with an internal audit, but this is important. And in the future, of course, there is the formal verification. That's a huge topic, but it's also in the roadmap somehow. Okay. Of course, as I mentioned, everything is open source. It's a repo. You can test it here, push it here, and we have also. I mean, just feel free to contact us for anybody that's trying it. If you have any problem, please feel free to contact us. We want to keep improving it and being at least one of the reference ZKVMs in the space. So that's very much. Thank you very much for listening to me.